Hello there, I'm Ehsan Karim. I've been using R for more than a decade and teaching it for more than 4 years. Welcome to the video course R Graphics Essentials. The software R is freely available, yet drawing statistical graphs is one of its greatest strengths that beats even most of the commercial packages. This course is a beginner's course to learn about R graphics. It offers an interactive, visual, and practical approach to learn how to create statistical graphs in R. The R Graphs Essential course doesn't require you to be a statistician or a programmer proficient in any other graphical package. If you are familiar with the basics of R and have a very basic statistical knowledge, you should be able to follow along. This course is divided into 8 sections. Each section is concise and has 5 segments. The segments are ordered by the level of complexity. The course starts from very basic R plot function, exploring enough time to gain control of this function. This course covers the plots for categorical and continuous variables. This course subsequently moves towards various plotting functions for bivariate and time series variables, eventually covering advanced 3-dimensional and interactive plots. Even though the main focus is to guide you through default R graphics capabilities, a few add-on packages are occasionally mentioned to guide you to further advanced functionality of R graphics. Through this course, I hope to help you learn the best techniques and code to create the statistical graph in your mind using R in the best way possible. Now, let's go and have fun learning how to draw informative statistical plots to effectively visualize your data using R. In this segment, we will use this BOD dataset. This dataset is included in a default package in R. First, let us look at the dataset BOD. It has 2 variables, time and demand. In an evaluation of water quality, this dataset has biomedical oxygen demand measurement. Corresponding times are also recorded. Using R graphics, we want to find out whether there is a relationship between the demand of biomedical oxygen with the recorded time. In order to do so, we plot the most basic type of plot, which we call scatter plot. In R, there is a function called plot that can help us draw the scatter plot of demand and recorded time. Let us see how. In the scatter plot, to have demand in the vertical axis and time in the horizontal axis, we use plot command to draw plot of demand and time from BOD data. In the R graphics window, we get a scatter plot. However, if we want a line instead of scattered points, we can press up button and add option type is L or line. To bring back the scattered points instead of line, we can put P or points as type. To draw both line and points at the same time, we can put B or both as type. To make the graph more informative, we need to have titles, subtitles, labels of both axes. In order to insert title, we include the parameter main. Similarly, to include subtitle at the bottom of the graph, we include the sub parameter. To insert horizontal and vertical axis labels, we include xlab and ylab parameters. In summary, we use the plot function in R to draw scatter plot between biomedical oxygen measurements and recorded time. Furthermore, we used various parameters to insert labels and titles of the scatter plot. Now, you will be able to draw a basic scatter plot in R. In the next segment, we will learn about putting legends and setting margins in a plot. In the previous segment, we discussed how to produce a basic plot in R and add necessary titles in it. In this segment, we will learn how to add legends on plots and adjust the margins of the plot. To demonstrate this, we will use a default R dataset called VA deaths that includes 1940s death rates of urban-rural population per thousand in Virginia. Let us take a look at the dataset VA deaths. Using our plot, we will plot rural deaths versus age and we will stratify the rates with respect to gender. In order to differentiate the lines produced for male and female death rates, we will learn how to insert the legends to make the graph more informative. Additionally, we learn how to fix the margins of the plot. In R, there is a function called legend that can be used to add legends to plots. Another function par can help us adjust the margins. Let us see how. We will reuse the commands in this segment. For this purpose, R script is a great tool. To open a new script file window, go to File menu and then select New Script. Since we will be using the rural death rates, we only need first two columns of VA deaths dataset. Let's create male and female death variables. To plot against the death rates, we need age group midpoints. Let us create them using a sequence command. Then draw the plot of age and male deaths using the type, xlab, ylab options that we learned in the previous segment. The new argument that we are going to use here is pch, which will make the points to be displayed as m in the line. To run these commands in R, we select a number of commands we want to run and then we press Ctrl R to submit it. Now, we use lines command to overlay the female death rates with f as pch argument. This will create a separate line is the same plot window. Now, to make the graph self-explanatory, we need a legend that will indicate that M stands for male and F stands for female in the graph. To add a legend, we use the legend function with first argument specifying the position of legend box. Legend argument specifies the words to be shown and then the title and corresponding PCH specifications are stated. To set margin, we use mar argument in the par function. The new margin will be effective when a new plot is drawn. But setting zero margin in all sides truncated all the axis levels. We need to keep some space in the bottom and left for making the axis levels visible. In summary, we used legend function to add legends of a plot. Furthermore, we used par function with mar argument to set margins of that plot. Now, you will be able to draw a basic plot with legends and set suitable margins of it. In the next segment, we will learn about putting text and mathematical expressions in a plot. In the previous segment, we learned how to put legends and adjust margins. In this segment, we will learn how to insert text and mathematical expressions in a plot. For this, we will use the default R dataset women. It has two variables, height and weight. Let us save these variables as independent objects in R. Using these variables, we will draw a scatter plot and add text and equations in it. Let us see how. First, we draw a plot with appropriate axis labels. To add a text in it, we use the function text. First, we need to specify the coordinates where we want to put the text and then the actual text. To insert a title after issuing a plot command, we can use the function title with argument main. Similarly, sub-argument in title function can be used to produce a subtitle. To insert mu as subtitle, we use expression function. Inside the plot boxes, if we want to write a text mixed with mathematical expression, paste function is a very useful one. First, save the whole expression as an object text, and then insert the object in a text function specifying the coordinates. Similarly, to write a whole equation inside the plot boxes, we use bquit function. Here, we write the equation of mean and save it as object equation, and then we add this equation in the plot using text function. In summary, we use the text function to insert text in a plot. Furthermore, expression and bquit functions were utilized to add mathematical notations and equations in a plot. Now, you will be able to insert text and mathematical expressions in a plot. In the next segment, we will learn about changing symbols and colors in plots. In the previous segment, we learned how to produce a basic plot in R and add necessary titles in it. In this segment, we will learn how to change symbols and colors in a R plot. To demonstrate this, we will again use the default dataset VA dates used in section 1 segment 2. Previously, we used this dataset to show the use of PCH argument to make the points look like English letters such as M and F. In this segment, we will see various other uses of PCH argument. We will also learn how to change colors to distinguish the lines. In R, we will use PCH and color function to change symbols and colors within a plot function. At first, we open a new R script from the file menu. We create the gender-specific rural death rate variables, male deaths, female deaths, and the age group midpoints. Now, we draw the plot of age and male death using the PCH equals 1 option. This will produce round symbols for the given points. Now, we draw the line of age and female deaths using the PCH equals 2 option. This will produce triangular symbols for the given points. Similarly, we could try various numbers of PCH to produce plots with various symbols. This looks nicer than representing points as English letters. To add a legend, we use the function legend with first argument specifying the position of the legend box. Legend argument specifies the words to be shown, and then title and corresponding PCH specifications are stated. In addition to a point in the legend, if we want a line in the legend as well, we specify LTY option there. To differentiate between lines, changing colors could be another nice feature. In order to do so, we use color argument instead of PCH in the plot function and make the line red. Similarly, we can do it for the lines function as well with green color. The legend can be modified accordingly. In summary, we use different symbols and colors to differentiate various lines in a plot. The corresponding arguments are PCH and call respectively. Now, you will be able to draw a plot with various symbols and colors. In the next segment, we will learn how to save R plots in various formats. In the previous segment, we learned how to use various symbols and colors to make a graph look beautiful. In this segment, we will learn how to save graphs in various formats. For this, we will again use default R dataset women that we used in section 1, segment 3. In R, we will use menu to save graphs. We will also see some R commands to do that without using menu options. First, open a new script from the File menu. Then, we use the plot command to draw a scatter plot of height and weight of women in that dataset. Then we first select the plot window, go to File menu, then Save As. This will give us the options to save the graph as metafile, script, PDF, PNG, BMP, TIFF, JPEG in various quality. Say, for example, I decide to save the plot as PDF. A new window will pop up asking me to decide a location and name to save the file. Browse to any folder where we want to save the file. Once we provide a name and press save, the file will be saved. Check the folder for example1 file. We can similarly save the R graphs using PDF, PNG, PostScript commands. For example, let us try PDF command. First, provide the location and name of the file where you want to save the graph. Plot it in R. This will not show any plot window since the plot is being drawn on a PDF device now. And check the folder for example 2. In summary, we used menu and R commands to save a graph. Now you will be able to save a graph in a specified format. In the next section, we will learn about further control of plot function in R. In the previous section, we learned about basic plot function and some of its argument in R. In this section, we will learn how to customize the plot by controlling axes and boxes of the plot. To demonstrate this, we will again use the default R dataset women used in previous section. In R, we will utilize functions such as box, axis, mtext to make appropriate adjustments. Let us see how. First, we open the R script from File menu. Using plot function and axis labels, we can draw a basic plot. To be able to customize a plot axis and box, we first draw a plot without any axis and box. This is done by setting axis option as false. Then we use box function to bring back the box. To bring the horizontal axis scale, we use the axis function with side equals 1 option. The label of the axis can be inserted in the margin by mtext function. To allow adequate space from the scale, we set line equals 3. Similarly, we can do this for the vertical axis. In order to customize the default tick marks, we use add and labels arguments in the axis function. In the vertical axis, to make the vertical tick marks horizontal, we use last argument in the axis function. Sometimes adding vertical axis in the right side helps us visualize better. In that case, we set fourth side on the axis function. In summary, we used box, axis, mtext functions to make appropriate adjustments in the axis. Now you will be able to customize the axis in the R plot. In the next segment, we will learn how to control the layout of the plot window. In the previous segment, we learned how to customize the axis of a R plot. In this segment, we will learn how to control the layout of a R plot window. To demonstrate this, we will again use the default R dataset women. In R, we will use mfrow argument in the par function and layout function to adjust the rplot layout. Let us see how. Let us first open the RScript window from File menu. We will draw histograms of height, weight, and then scatter plot of height versus weight. Note that once we draw another plot, the previous plot is overlapped by the new one. To be able to draw the plots in the plot window, we use mfrow option in par function. Here, we set 2 rows and 1 column. To accommodate 3 plots, we use 2 rows and 2 columns. However, we can see there is one plot spot blank in the last row. To adjust this, we use a matrix lay.mat to set 2 plots in the first row and then 1 plot in the last row. By row argument suggests that the elements will be inserted by row in the matrix. Then we use this matrix in the layout function to set the layout. Now we can see the plots will be inserted as instructed. Then if we draw a new plot, we will see that it is shown in the pre-specified layout format. Therefore, we need to reset the layout before plotting the next one. In summary, we can use mfrow argument in the par function and layout function to customize the rplot layout. Now, you will be able to adjust the layout of the rplot window. In the next segment, we will learn how to control the colors of different plot elements. In the previous segment, we learned how to adjust the layout of a rplot window. In this segment, we will learn how to adjust the colors of various rplot elements. To demonstrate this, we will again use the default R dataset women. In R, we will use call argument of plot, box, and axis functions. First, we plot a default R plot of height and weight of women. Here, by default, the color of all the elements are black. As we have seen before, we can change the color of the scatter plot points by call arguments. In order to change the color of title, we use call.main argument in the plot function. The same thing can be done using call.main argument in the title function. To change the color of access labels, call.lab argument can be used in the plot function. To change the color of the box, call argument in the box function can be used. Similarly, the access colors can be modified using the call argument in access function. In summary, all the elements in rplots are customizable. We can change the color of any rplot element. Now, you will be able to make necessary color adjustments to plot elements. In the next segment, we will learn how to change the line patterns and widths. In the previous segment, we learned how to change colors of various rplot elements. In this segment, we will learn how to change the line patterns and widths. To demonstrate this, we will again use the default R dataset VA dates that we used in the earlier sections. As usual, we define male and female death variables and corresponding age group midpoints. In R, we will use LTY and LWD arguments in plot function to change the line patterns and widths. Let us illustrate this with an example. First, we draw a plot of male death rates versus age group midpoints with line type as 1. We draw another line of female death rates with line type as 2. Note that the two lines are easily distinguishable. Then we choose appropriate legends for them. Similar to line type, we can try various widths of lines. For more lines, we can choose more line types and widths. In summary, we can draw plots with various types and widths of lines. Now, you will be able to draw lines with distinguishable types and widths in our plot. In the next segment, we will learn how to control text sizes, colors, and fonts of the plot elements. In the previous segment, we learned how to change the line patterns and widths. In this segment, we will learn how to control text sizes, colors, and fonts of the plot elements. To demonstrate this, we will again use the default R dataset OMEN. In R, we will use call, sex, and font arguments in plot function to control text sizes, colors, and fonts. First, we plot the height and weight of the OMEN with a title. To change the font size of the title, we can use sex.main option. Similarly, to change font size of the access levels, we use sex.lab. Same thing can be done for texts inserted in the plot. We can change the color of text using the call argument of text function. Also, to change the font size of the inserted text, we can use the sex argument of the text function. Sometimes having the access label in the right side also may help visualizing the data points. In that case, we use mtext function. Additionally, we can adjust the font of the title. Similarly, to make the title bold, we can use font.main equals 2. Similarly, to make the title italic, we can use font.main equals 3. In summary, we used various arguments of plot, title, text, mtext function to adjust text elements of our plot. Now, you will be able to control text sizes, colors, and fonts of the rplot elements. In the next section, we will learn how to draw plots to describe categorical variables properly. In the previous section, we learned how to control various arguments of basic plot function. In this segment, we will learn how to create a pie chart using one variable. To demonstrate this, we will again use the default R dataset VA deaths. In particular, we will use the death rates from rural male. Later, we will need corresponding age group names and number of groups. Let us save them as variables. In this segment, we will use this dataset to create a pie chart. In R, we will use pie function to create a pie chart. Let us see how. At first, we use pie function on the rural male variable. This will create a basic pie chart. By default, the labels are attached with the corresponding portions of the pie chart. Also, various groups can be distinguished by different default colors. To add titles, we can add the main and sub arguments. Now, if we want to modify the names of the groups in the pie chart, we can create the appropriate labels and then apply it in the pie chart using the labels argument. To customize the colors, we can set preferred colors using call argument. To get rainbow colors, we can use rainbow function. In general, the groups are ordered in an anti-clockwise fashion. To have the groups ordered clockwise, we can use clockwise argument. In summary, we use pie function to draw pie chart. We can customize it using various arguments such as labels, call, etc. Now you will be able to draw a pie chart from a given variable. In the next segment, we will learn how to draw a bar chart. In the previous segment, we learned how to create a pie chart in R. In this segment, we will learn how to create a bar chart using one variable. To demonstrate this, we will again use the default R dataset VA deaths. In particular, we will use the death rates from rural male. Later, we will need corresponding age group names and number of groups. Let us save them as variables. In R, we can use barplot command to produce a bar plot. Let us see how. Let us apply barplot function on the rural male variable. This will produce bar plot with vertical bars. To make the graph more informative, we can add title and subtitle to it. To make the bars horizontal, we can use the horiz argument. If we wish, we can customize the color of the bar plots. For example, here we use dark green color to fill all the bar plots. It is also possible to add multiple colors to each bars. Similarly, the legends can also be placed using the legend argument in the barplot function. Otherwise, we can use legend function separately. This will give us more control of where we want to place the legend. In summary, we can use barplot function and its various arguments to draw a bar plot. Now, you will be able to draw a bar plot. In the next segment, we will learn how to draw simultaneous bar plots with more than one variable. In the previous segment, we learned how to create bar plot using one variable. In this segment, we will learn how to draw bar plot of multiple variables simultaneously. To demonstrate this, we will again use the default R dataset VA deaths. Later, we will need corresponding age group names and number of groups. Let us save them as variables. In R, we will again use barplot function. Previously, we applied barplot function to only one of its variables. This time, we apply the barplot function on the whole VA-Deaths dataset. We can also determine the colors. For more harmonious color schemes, we can use heat colors. Or we can use the rainbow color schemes as before. To make the plot more informative, we can add titles to it. If side-by-side bar plots are not preferable, we can use stack version of it by setting beside argument as false. It is possible to make the graph horizontal as well. Same can be done when we have side-by-side bar plots. In summary, it is possible to graphically represent multiple variables in R using bar plot. Now, you will be able to draw bar plot with multiple variables. In the next segment, we will learn how to label pie charts and bar plots. In the previous segment, we learned how to draw bar plot using multiple variables. In this segment, we will learn how to label pie charts and bar charts. To demonstrate this, we will again use the default R dataset VA-Deaths. In particular, we will use the death rates from rural mail. Later, we will need corresponding age group names and number of groups. Let us save them as variables. Additionally, we will use percent form of the data as labels. Therefore, we convert the values to percent and create corresponding label variables with percent sign. In R, we will use paste function and labels arguments to create and apply the labels. Let us see how. First, we create a pie chart with titles, subtitles, color, and also set the order pattern using clockwise argument. To add percent labels, we use the created percent values in the label argument. To apply similar labels in bar chart, we first need to save the plot as an object. To add the labels, we use text function. If the limits are not properly set, then we customize the limits. To add the percent labels, we need to determine the labels first, then apply them. Here, we also set the position of the label to accommodate a space between the bar and the text. In summary, we used labels argument to apply the labels in the pie chart and bar diagram. Now, you will be able to customize the labels in the plot. In the next segment, we will learn how to draw dot charts. In the previous segment, we learned how to label pie charts and bar plots. In this segment, we will learn how to draw dot plots in R. To demonstrate this, we will again use the default R dataset VA-Deaths. Later, we will need corresponding group names and age group names. Let us save them as variables. For convenience, we will also assign names to each variable in the dataset. In R, we can use dot chart function to draw dot charts. Let us put rural mail variable in the dot chart function. We also set the labels and the patterns of the points. To have a generalized dot plot with all the variables in the dataset, let us combine the variables into one. Then repeat group numbers and age group names. Using them, we can create a dot plot that can accommodate the whole set of data. Additionally, we use titles, labels, and colors. A legend can be placed to make the plot more informative. In summary, we can use dot chart function in R to draw a dot plot. Now, you will be able to draw a dot plot and customize it. In the next section, we will learn how to create plots for continuous variables. In the previous section, we learned how to create plots for categorical variables. In this segment, we will learn how to produce a stem and leaf display using R. To demonstrate this, we will use the default R dataset chick weight in all segments of this section. For this purpose, we will need body weight of the chicks in gram when the chicks received the experimental diet 1 and 2. We create two separate variables WDT1 and WDT2 for convenience. In R, we will be using the function stem to produce the stem and leaf plot. Let us see how. At first, let us open the R script. We use the stem function on the body weight of the chicks when they received the experimental diet 1. To find out the arguments of this function, we find the associated help file from R using help function. To adjust the plot length, we can use the scale argument. For example, when we set scale equal to 2, the number of stems increases. We can also adjust the width or length of leaf of the plot using width argument. Stem is a function from default R graphics package. Another useful package is APLPack. In this package, we can find additional functions related to stem and leaf plot. Let us first install the package. We select appropriate mirror. After installing successfully, we load the package using require function. In the new package, we can use stem.leaf function to draw the stem and leaf plot. If we need to compare two variables, we can use back-to-back stem and leaf display. For example, the body weight of the chicks when they received the experimental diet 1 and 2 can be compared using this function stem.leaf.backback. To construct two parallel stem and leaf displays side by side, back-to-back argument can be used. In summary, we can use stem function from graphics package and stem.leaf and stem.leaf.backback function from APLPack package to construct stem and leaf plots. Now you will be able to draw stem and leaf plots in R. In the next segment, we will learn how to construct a histogram. In the previous segment, we learned how to construct a stem and leaf display. In this segment, we will learn how to construct a histogram. To demonstrate this, as last segment, we will use the default R dataset chick weight and associated variables. In R, we will be using the function hist to produce the histogram. Let us see how. At first, let us open the R script. We use the hist function on the body weight of the chicks when they receive the experimental diet 1. We can adjust the horizontal axis label and title by using xlab and main arguments. To specify the number of cells in the histogram, we can use the breaks argument. Same argument can be used to specify the vector of breakpoints between the cells. We can change the bin size as we wish. This is an example of equi-spaced breaks. If this histogram is a graphical representation of probability densities, we can use probability or prob argument. To change colors of all cells of the histogram, call argument is used. To assign different colors to different cells, same argument can be used. To get rid of the cell borders, border argument is used. It is possible to assign non-equi-spaced cells in the histogram by setting the breaks properly. If shading lines are preferable to cells, density argument can be used. The histogram can also be saved as an R object. For example, here we are saving it as hist.obj. We can list the components of this object using names function. For further detail of this function, we can see the help file of the hist function. In summary, we can use hist function and various arguments to construct a histogram. Now, you will be able to draw a histogram in R. In the next segment, we will learn how to draw density plot, RAG representation, and overlay plots. In the previous segment, we learned how to draw a histogram. In this segment, we will learn how to draw a density plot, RAG representation, and overlay plot. To demonstrate this, we will again use default R dataset, cheek weight, and its associated variables. In R, we can use various functions such as RAG, lines, polygon, curve functions to achieve the objectives. At first, let us open the R script. The density of body weight of the chicks when they receive the experimental diet 1 can be obtained using the density function. We use the plot function on the density. The RAG representation of data can be placed under the graph by RAG function. If desired, the RAG function can be placed above the graph as well using the side argument. To show an example of overlay plot, let us first draw a histogram of body weight of the chicks when they received the experimental diet 1. Then the density can be plotted using the lines function. Same objective can be achieved using the polygon function. If it is desired to compare a density of the data with a curve of a given theoretical density, we can use curve function. In this example, we are comparing the density of body weight with a given gamma distribution. In summary, we can use plot and density function to draw a density plot. RAG representation can be obtained by RAG function. Lines, polygon, and curve functions can be used to draw overlay plots. Now, you will be able to draw a density plot, RAG representation, and overlay plot in R. In the next segment, we will learn how to draw a box plot. In the previous segment, we learned how to draw a density plot, RAG representation, and overlay plot. In this segment, we will learn how to draw a box plot. To demonstrate this, as last segment, we will use the default R dataset, cheek weight, and associated variables. In R, we will be using the function boxplot to produce the box and whisker plot. Let us see how. At first, let us open the R script. We use the boxplot function on the body weight of the chicks when they receive the experimental diet 1. To increase the width of the box, we can use the box weights argument. To decrease the width of the box, we can assign a smaller value for the box weights argument. To draw a notch in each side of the boxes around the median, notch argument can be used. To get rid of the outlier values, outline argument is used. To make the plot horizontal, horizontal argument is used. Change the sign representing the outliers, we can change the values of outpch argument. To see additional help files associated with the boxplot function, we can take a look at the associated help file. The numerical statistic values associated with the boxplot can be obtained by boxplot.stats function. In summary, we can use boxplot function to draw a box and whisker plot. Now, you will be able to draw a boxplot in R. In the next segment, we will learn how to plot side-by-side boxplot. In the previous segment, we learned how to draw a box plot from a variable. In this segment, we will learn how to draw side-by-side box plots when multiple variable is present. To demonstrate this, as last segment, we will use the default R dataset, chick weight and associated variables. In R, we will again use the boxplot function to produce side-by-side box and whisker plot. Let us see how. At first, let us open R script. We use the boxplot function on the body weight of the chicks when they receive 4 kinds of experimental diets. To be able to control the axis and associated labels, we can use the axis function. To work with only part of the data, say for example, body weight of the chicks when they receive first 2 kinds of experimental diets, we can use subset function. We can use the boxplot and axis function on these reduced data to produce 2 box plots to compare the outcome of these 2 diets. To make the boxplot widths proportional to the square roots of the number of observations in each chick group, we can use the varWidth argument. To color the boxes, we can use a vector of colors in call argument. For example, here we are using 4 colors from rainbow function. Just like histogram, we can also save the boxplot as a R object. This object saves various statistic values corresponding to the plot. Such information can be used to improve the quality of information shown in the plot. For example, here we are showing the number of chicks in each diet group. Additional arguments can be used to control various components of the boxplot, such as median, whisker, staples, outliers, etc. In summary, we can use boxplot function to draw single or side-by-side box plots. Now you will be able to draw box plots in various scenarios. In the next section, we will learn how to draw plots for bivariate data. In the previous section, we learned how to plot continuous variables. In this segment, we will learn how to draw bivariate plots using 2 continuous variables. To demonstrate this, we will use the default R dataset US arrests that contains 1973 arrest statistics per 100,000 residents in the US states for assault, murder, and rape. In R, we will be using plot and scatterplot functions to draw bivariate scatterplot. As shown in an earlier section, we can use plot function to get a scatterplot of two variables. In this dataset, we will use the column assault and murder. When we use tilde in the formula of this plot, it means assault is in the horizontal axis and murder in the vertical axis. Another useful function is scatterplot function from car package. Let us install the package first and then load it. This package has a lot of arguments. Let us bring the basic plot first. To draw grids in the background, we can set grid equal to true. Sometimes it is helpful to see a one-dimensional projection of a two-dimensional dataset. To get such a plot, we need to use boxplot2d function in the APL pack package. Let us install and load the package first. Then, boxplot2d function can be used to get the projection. Using the same package, we can get a bivariate generalization of the box plot from the backplot function. In summary, we can use plot and scatterplot function to create scatterplots from bivariate data. Additionally, boxplot2d and backplot can be used to summarize bivariate data. Now, you will be able to summarize bivariate data using scatterplot and other tools. In the next segment, we will learn how to add straight lines and jitter points in the scatterplots. In the previous segment, we learned how to draw scatterplot and other plots to summarize bivariate data. In this segment, we will learn how to add straight lines and jitter points. To demonstrate this, we will use some simulated variables. The first variable is x, contains the values 0 and 100. These values are duplicated 10 times. Another variable y is a random sample of size 20 of values from 1 to 10. In R, we will use abline and jitter functions to add lines and jitter points respectively. Let us create the scatterplot first. Due to data duplication, some of the values are overlapped and can be identified separately. One solution is to introduce a small amount of noise in the data so that the identical values can be seen separately. To do that, we use the jitter function. To make the points closer, we can adjust the values of the argument factor. To make them distant, we can increase the value. Jittering points can be again created via the scatterplot function of the car package. To add a vertical line at the 50th unit of the vertical axis, we can use abline function with argument v equals 50. Similarly, to add a horizontal line, argument h can be used. If a partial line is desired, we can use segments function, specifying the coordinates of the line start and end points. A similar command is arrows that can do the same. Both of these type of lines can have some angle if desired. They don't have to be either horizontal or vertical. In summary, we can use jitter to jitter the points and abline segments arrows function to draw straight lines. Now, you will be able to jitter points and draw straight lines. In the next segment, we will learn how to add model summaries in a scatterplot. In the previous segment, we learned how to add straight lines and jitter in a scatterplot. In this segment, we learn how to add model summaries in a scatterplot. To demonstrate this, we will again use the default R dataset US arrests. In R, we can use plot, scatterplot, AB line, Loess, predict, residuals, etc. functions to add model summaries in a plot. We plot the data via a scatter plot using plot function. Then we feed the regression model using the associated variables. We save the model fit as a R object. Then the object can be used in the reg argument of abline function. This will place the regression line in the scatter plot. Same plot can be directly obtained from the scatterplot function of the char package. This doesn't require us to feed the regression model and save it as an object prior to running this command. Additional smoothing or non-parametric regression line can be added by setting smooth argument as true. It is possible to produce this smoothing line while using plot function. In that case, we need to use Loess function. Another similar but newer function is Loess. The function scatter.smooth can be used to utilize it. To insert numerical summaries inside a plot, we can combine character and numeric values using bivariate function. To insert these in a plot, we use text function. One useful plot for regression diagnosis is a plot of independent versus fitted values. Another such plot is residual versus fitted values. This can be created using the scatter.smooth function as well. Default plot function can also be used to generate several of such diagnostic plots. In terms of showing model summaries, the function scatterplot produces both linear and smooth regression in the plot by default. Additional univariate box plots can also be generated on the margins. This can also be an useful tool to check diagnosis of the regression. In summary, we can use plot, scatterplot, abline, scatter.smooth functions to place model summaries in a scatter plot. Now, you will be able to add necessary model summaries in the plot as well as check model diagnostics. In the next segment, we will learn how to subgroup points within a scatter plot. In the previous segment, we learned how to add model summaries in a scatter plot. In this segment, we will learn how to subgroup points in a scatter plot. To demonstrate this, we will again use the default R dataset US arrests. In R, we can use basic plot function or scatter plot function to subgroup the points in the data according to a given subset. First, let us fit one regression line based on subgroup of at most 50% urban population. The second regression line will be based on subgroup of above 50% urban population. We name these fits as fit 1 and fit 2 respectively. We set the margins so that we have enough space to accommodate multiple plots. Then the layout is set such that two plots can be placed in the first row and the overall single plot can be plotted at the bottom. Using scatter.smooth and abline function on fit 1, we can place both linear and smooth regression lines in the scatter plot. Same can be done using second subset and the object fit2. To produce the final overall plot with distinguishable points from different subgroups, we create the plot step by step. First, we produce a blank plot. Then we add points from first subgroup using points function. Similarly, we add points from second subgroup. Titles access boxes are placed. Plot access labels are placed. Legends are placed appropriately. Finally, the model summaries from the overall data are placed. This was a useful exercise using the plot function. However, all the contents of these plots can be condensed in one plot if it is created using the scatterplot function with suitable condition. In summary, we can use points function to separately insert different subgroups points. Now, you will be able to subgroup the data points in a plot based on appropriate conditions. In the next segment, we will learn how to produce scatterplot matrix based on condition. In the previous segment, we learned how to subgroup the data points in a plot based on appropriate conditions. In this segment, we will learn how to produce scatterplot matrix based on condition. To demonstrate this, we will again use the default R dataset US arrests. In R, we will use functions such as pairs, scatterplot matrix to produce scatterplot matrix. A unconditional scatterplot matrix can be produced by using pairs function. To replace condition, we have to produce a logical vector based on given condition. For example, we are using if-else function here to produce the condition variable. Then we use this condition on the pairs function to get the scatterplot matrix, where point colors and associated signs are based on given condition. This can also be accomplished from the scatterplot matrix function of the car package. In summary, we can use pairs and scatterplot matrix function to produce scatterplot matrix. Now, you will be able to draw a scatterplot matrix in R. In the next section, we will learn how to deal with time series plots. In the previous section, we learned how to draw bivariate plots in R. In this segment, we will learn how to plot basic line graphs. To demonstrate this, we will use the default R dataset air passengers to show how to deal with line graphs in R. In R, we will again use plot function to do that. First, let us check the class of the dataset air passengers. This is a TS object. That means the data here are time series like objects. To draw line per year, we need to extract partial data from this object. For convenience, we can convert this time series object to a matrix using the matrix function by setting column number. R will automatically adjust the row numbers based on the number of available data. Also, we need to specify in which order the matrix should be filled. Now, we can plot each year's data conveniently. To have good control on the plot, we choose not to put the default axes and also clear the axis labels. The vertical axis is numerical, so we set it as usual. Also, we set the vertical axis label. To get month names in the horizontal axis, we use month.abb as labels in the axis function. Here, last equal to 2 will have the month names vertical, so that we can accommodate more space for each of the months. After adding the second line, we realize that we don't have enough space in the plot. Hence, the second year's line gets truncated at the top. To fix this, we set the volume argument so that no matter which year's data is used, the line will not be truncated. We also set a legend accordingly. Instead of having the month names vertical, one could prefer to have them slightly angled. One trick could be to set blank labels in the horizontal axis and then use text function to place them there after adjusting the angle of the month names. In summary, we can use plot function to draw the line plots of a time series. Additionally, we can use axis and text function to adjust the axis labels of the time units. Now, you will be able to draw a line plot in R. In the next segment, we will learn how to draw time series plot. In the previous segment, we learned how to draw line plots in R. In this segment, we will learn how to draw default time series plots. To demonstrate this, we will again use the default R dataset air passengers, which contains time series. In R, we can use TS window functions to deal with time series. For drawing corresponding plots, we can use ts.plot, SCF, PSCF, and plot function. Let us see how. First, let us take a look at the dataset air passengers. Here, we can see observations collected at each month of the years 1949 to 1960. There are some time series functions that we can use to summarize the index time. Cycle function shows the position in the cycle of each observation. The first and last time index can be seen using start and end functions. Frequency functions show number of observations per year. TSP function shows all of this information together, start and end years and the frequency. As air passengers is a time series object, we can simply use plot function to plot the series. In the previous segment, we converted the time series to a matrix to extract the partial information from the series. In this segment, let us show how we can extract partial information from time series itself. For that, first, obtain the size of the series. Using this information, we divide the series and then convert it back to time series using TS function. Now, to plot both of these series in the same time axis, we can use ts.plot function. We can also use call argument to distinguish the colors of the series. However, if we want to preserve the original time axis, we can use window function to specify the time series windows by which the series should be divided. In this example, we divide the series at the end of 1954 and make them separate series. Now, if we plot these two series using ts.plot, they are drawn in their original time axis. R also allows us to draw some basic time series plots by default. For example, we can use SCF and PSCF functions to draw autocorrelation and partial autocorrelation respectively. The zoo package has some additional time series handling functionalities. For example, we can separate the data and time index of a time series using core data and index functions. Using this information, we can fit linear models and use the information to reduce trends of a series. Additionally, we can use forecast package. This enables us to fit exponential smoothing state space and ARIMA models via the functions ETS and auto.arima. Plotting the output of forecast function, we can get the corresponding predictions from the models. For example, here we are forecasting 10 years ahead. In summary, we can use R and other packages such as do and forecast to draw plots using time series. Now you will be able to draw time series plots. In the next segment, we will learn how to plot date and time variable. In the previous segment, we learned how to draw time series plots. In this segment, we will learn how to plot date and time variables. To demonstrate this, we will again use the default R dataset AR passengers. In R, we will use axis.date, axis, and format functions to appropriately use date and time variables in a plot. Let us see how. First, we use core_data function of zoo package to extract the observations of the data. For convenience, we will just use observations from only first year. As we have seen before, using start function, we can extract the first date. As with numeric data, we can also use sequence function to generate the sequence of dates. We need to define first and last date and the length of the sequence. Alternatively, we can use by argument. First, we plot the time series where horizontal axis ticks are not set. Then, we use format function to extract the month. To get names of the months, we use month.abb object default in R. Finally, we use the created label in the axis.date function to fill the horizontal axis. To accommodate all the month names, we can use last argument. In summary, we used axis.date and format functions to appropriately use date and time variables in the plot. Now, you will be able to use date and time variables suitably while plotting. In the next segment, we will learn how to plot trends. In the previous segment, we learned how to plot date and time variables. In this segment, we will learn how to plot trend. To demonstrate this, we will again use the default R dataset AR passengers. In this segment, we will use aggregate, STL, month plot, season plot functions to plot trends. Let us see how. Let us plot air passengers data. Then we use the aggregate function to split the data by year and compute mean for each. We then use line function to put the mean observations in the plot. As before, we can fit the series using a linear model on the time index and calculate the residuals. We can then use the aggregate function to calculate the mean observations per year and plot them in the actual and residual plot. This shows the yearly summary pattern of the detrending. To see the overall pattern by a line, we can do the same using the lowest function. We can draw seasonal plots using STL function by defining periodic window. Similarly, using STLF function from the forecast package, we can forecast the STL objects. We can also use month plot function to draw seasonal plots directly. One other option is to use season plot function from the zoo package. In summary, we can use aggregate, STL, month plot, season plot functions to plot trends and draw season plots. Now, you will be able to draw these lines and plots in R. In the next segment, we will learn how to set appropriate time axes. In the previous segment, we learned how to draw trends. In this segment, we will learn how to set up appropriate time axes. To demonstrate this, we will again use default R dataset air passengers. In R, we will use axis.date, axis, and format functions to appropriately set time axes. Like before, we will use core data function of zoo package to extract the observations of first 2 years and make an index of these 2 years by month. Plot these variables using plot function. Then we use the axis.date function to fill them as we have learned in the previous segments. But if we follow this procedure, time axis is too busy to read. Using as.yearmon function, we can assign them, but that might be too much text in the axis. In that case, format function can be used to extract the months, whereas January's would be replaced by year. This can be inserted in the axis using axis function. In summary, we used axis.date, axis, and format functions to appropriately set time axis. Now, you will be able to set up appropriate time axis in a time series plot. In the next section, we will learn how to plot contour plots and 3D plots. In the previous section, we learned how to draw time series plots. In this segment, we will learn how to draw contour plots. To demonstrate this, we will use the default R dataset Volcano, which contains topographical information for Mauna Kea volcano in Auckland. In R, we will use image and contour functions to draw image and contour plots. Let us see how. Let us see the dimension of the volcano data. The image function can be used to draw grid of colored rectangles where colors corresponding to the supplied spatial data or images. By default, heat colors are used to color the plot. There are other color palettes that we can use. For example, we can use terrain colors, CM colors, topographical colors, or rainbow colors. To get contour, we use contour function. We can also adjust the contour by its arguments. Putting color palette in call argument doesn't fill the contour. In order to do so, we need to use filled contour function. We can again use various color palettes and choose whichever is suitable. In summary, we can use image, contour, filled contour to create image and contour plots. Now, you will be able to draw these plots in R. In the next segment, we will learn how to draw contour plots in Lattice and other packages. In the previous segment, we learned how to draw contour plots. In this segment, we learn how to draw these plots in a fancier way using Lattice and other packages. To demonstrate this, we will again use the default R dataset Volcano. In this segment, we will use contour plot, level plot, SP plot function to draw contour and related plots. Let us see how. First, we load the Lattice package. To draw contour plot in lattice, we use the function contour plot. Level plots are drawn using level plot function. We can also omit the axis using scales argument. One other related package is raster. It depends on ArcGIS packages. We install both and load the raster package. We can create the raster layer object using raster function and then convert it to polygons. Using SPplot, we can plot this transformed spatial object. We can change the breaks to get more detailed layers. In summary, we can use contour plot, level plot, SPplot functions to draw contour plots. Now you will be able to draw these plots in R. In the next segment, we will learn how to draw surface plot. In the previous segment, we learned how to draw contour plots using various packages. In this segment, we will learn how to draw basic surface plots. To demonstrate this, we will again use default R dataset Volcano. In R, we can use parse function to draw surface plot. Let us see how. We apply parse function on the Volcano data. To change the viewing direction, we can use theta argument. Phi is another argument for similar purpose. To get detailed tick, we can adjust tick type argument. It is also possible to expand or shrink the box using the expand argument. It is possible to shade the plot using the shade argument. To draw point and lines, we can use points and lines functions as well. To show a much simpler example, we can generate data from multivariate t distribution using mvt-norm package based on given x and y values and save it as z object. Using XYZ objects, we can plot surface plot. In summary, we can use parse function to draw surface plot. Now, you will be able to draw a surface plot in R. In the next segment, we will learn how to draw fancier surface plots. In the previous segment, we learned how to draw basic surface plots using base package functions. In this segment, we will learn how to draw fancier surface plots using other packages. To demonstrate this, we will again use the default R dataset Volcano. In R, we can use wireframe, rotate wireframe, and surface 3D functions to draw fancy surface plots. Let us see how. At first, we install the lattice package. Then we use the wireframe function on Volcano data. This creates a surface plot. We can also use cloud function to do so. Another way we could get surface plot is by using rotate.wireframe function of the teaching demos package. This gives us a new menu to rotate the surface plot, which can help visualize the plot from various angles. Surface plots can also be generated using the surface 3D function from RGL package. Simply using mouse, we can rotate and enhance the plot. Using the same multivariate t distribution data that we have generated in the last segment, we can draw these interactive plots via the surface 3D function. In summary, we can use wireframe, rotate.wireframe, and surface 3D functions to draw surface plots. Now, you will be able to draw interactive surface plots. In the next segment, we'll learn how to draw interactive 3D scatter plots. In the previous segment, we learned how to draw surface plots. In this segment, we will learn how to draw 3D scatter plots. To demonstrate this, we will use simulated data. In this segment, we will use scatterplot 3D, cloud, plot 3D, scatter 3D functions to draw 3D scatter plots. Let us see how. First, we generate some data and save them as the objects x, y, z in R. Using the scatterplot 3D function of scatterplot 3D package, we can draw 3D scatterplot. We can also draw this by using plot 3D function from RGL package. To better visualize, we can change the color palette. To include lines, we can use lines 3D function. Another function to draw 3D scatter plot is the scatter 3D function from car package. Just for illustration, we applied these functions on the same multivariate t distribution data as we have generated in the last segment. In summary, we can use scatterplot 3D, cloud, plot 3D, scatter 3D functions to draw 3D scatter plots. Now you will be able to draw 3D scatter plots in R. In the next section, we will cover miscellaneous topics of R graphics. In the previous section, we learned how to draw contour plots. In this segment, we will learn how to draw maps. To demonstrate this, we will use various R datasets from the packages maps and map tools. In this segment, we will use the functions map, smooth.map to draw maps in R. Let us see how. First, we install and load the package map tools. We load the data wrld_simple to get data of a simplified world map. Using this data, we can draw world map using plot function. Similarly, using state.vbm data, we can draw US map statewide. Other packages, such as maps, also contain such geodata. For example, using map function, we can see country-specific maps as well. In this example, we are plotting the map of Italy. Using fill argument, we can fill the map with specific colors. Here, we are filling the map by red color. We can also fill using color palettes for different county of US. Specific county can be drawn as well instead of full US map. Respective names can be inserted using map.text function. If necessary, only selected states can be drawn by mentioning the names of the state. State-wise, map can also be drawn without the line for interior splits. Or we can also set boundary argument equal to false to get rid of the boundary, but keep the state splits. Of course, we can bring back the boundary by setting boundary argument equal to true. It is possible to identify various parts of the map by clicking. If we have any information categorized by geodata, then we can use such information to plot the map where the colors will depend on the information of the data. For example, votes.repub contains state-wise vote data in various years. In a given year, if we want to create a visual map by vote frequency, we can use map function to plot the area first, feed smooth.map to smooth the votes to calculate an average frequency of votes, and then draw image and field contour plots to display the colors based on the smooth averages of the votes. In summary, we can use maps and map tools packages to obtain geodata to plot maps of various regions. There are other packages with similar geodata information. Now, you will be able to draw maps in R. In the next segment, we will learn how to draw plots where we can interactively change the features of the drawn plot. In the previous segment, we learned how to draw maps. In this segment, we will learn how to draw plots where we can interactively change the features of the drawn plot. To demonstrate this, we will use default R dataset iris. We attach the iris data to be able to call the columns of this data directly as vectors. Previously, we used RGL package to be able to just rotate the 3D plots. In this segment, we will use iPlots package to show how to control some of the interactive features of R plots drawn via the package. Let us see how. First, let us see the identify feature of the basic R plot. We can identify any data by clicking on the data. Based on the identification information, we can pull the information from the data to take a closer look at the identified observation. Let us install and load the package iPlots. We can draw a bar plot using iBar function. Using menu, we can rotate it to get a horizontal bar plot. We can also apply various color palettes by selecting it from the view menu. We can also sort the bar by count. We can draw a box plot using iBox function. Using menu, we can rotate it to get horizontal box plot. We can also hide and show grids or axes. We can also sort the box plots by count or other values from menu. Using menu, you can rotate it, can apply various color palettes by selecting it from the view menu. We can also change bandwidth levels by pressing up or down button in the keyboard. iPlot function can be used to draw scatter plots. iABLine function can draw regression line fit inside the plot. Similarly, ilines function can be used to draw overlay line such as lowest fit line in the same plot. iText function puts text inside the plot. Background, axis range can be changed from the menu. Pressing up or down button in the keyboard, we can also control the size of the points in the plot. To recover the data used to draw the last plot, we can use the iplot.data function. Similarly, imap function can draw map objects. Parts of the map can be selected and colored. Border lines can be toggled. Parallel coordinates plots can be drawn using ipcp function. All these plots can be saved from the menu in a local file. In summary, we can use various functions from iPlots package to interactively control various features of a plot even after drawing it. Now, you will be able to draw and control interactive plots in R. In the next segment, we will learn how to use R Commander. In the previous segment, we learned how to draw and control interactive plots in R. In this segment, we will learn how to use graphical user interface version of R. It is known as R Commander. To demonstrate this, we will use the default R dataset IDs. In this segment, we will draw various basic R plots using just the menu of R Commander. First, we open R and install R Commander and load it. A new menu will pop up. In the script window, we write the command to load the iris data. Then we submit it. The command goes to output window. Now, click on the dataset menu where it says no active dataset. We can see the iris data listed here. We select it and press OK. The iris data is loaded in the R Commander, ready to be used. To view the data, press View Dataset. In case an edit is necessary, press Edit Dataset. Once the data is loaded, choose the Graphs menu. Select Index Plot, choose petal.length variable, select spikes. This will produce an index plot inside R. Also, note that the code for creating this plot is pasted in the output window. Select histogram from the Graphs menu, select a variable, set axis scaling, and a histogram will be produced. Select histogram from the Graphs menu. Select variable and a stem and leaf display will be printed in the output window. To create a box plot, choose box plot from the Graphs menu. We can also create quantile comparison plots by choosing the variable and the distribution name. Scatterplot can be created by choosing two variables from the scatterplot window. We can also choose to zitter, put log axis, draw box plots in the margin and insert various lines such as least squares, smooth fit, etc. It is also possible to set the size of the points, axis text, and axis labels. Scatterplot matrix can be drawn by selecting multiple variables. Strip charts can be drawn by selecting a factor as a dependent variable and a continuous variable as independent. In the same way, from the menu, we can also draw bar plots and pie charts. All these graphs can be saved from the Graphs menu in various file types as a local file. In summary, we can draw various basic R plots from the R Commander Graphs menu. Now, you will be able to use menu instead of command lines to create the basic R plots. In the next segment, we will learn how to draw trees based on clusters. In the previous segment, we learned how to draw R plots using R commander. In this segment, we will learn how to draw tree based on clusters or dendrograms. To demonstrate this, we will again use the default R dataset words.repub. In this segment, we will use hclass reg.hclass agnes functions to draw cluster trees or dendrograms. To perform hierarchical cluster analysis on a set of dissimilarities, we use hclass function on the loaded data. The complete agglomeration method was used to do this. We can plot this using the plot function. To draw rectangles around the branches of the dendrogram, we can use reg.hclass function to highlight the corresponding clusters. We can also draw this using words agglomeration method. The resulting rectangles around the clusters may be different. Similarly, agnes function of cluster package can be used to create a cluster tree. This object can be drawn as a dendrogram using pltree function. Alternatively, we can use plot function if this is converted as a dendrogram object before plotting. To see the labels clearly, we can make the plot horizontal and reduce the font size. To draw word hierarchical clustering with bootstrap p values, we can use pvclust package. This will show dendrogram with p values and rectangles can be added. Additionally, standard errors of AU p-values can be shown graphically using scplot. In summary, we can use hclass rect hclass agnes functions to draw clustering trees and dendrograms. Now you will be able to draw these plots in R. In the next segment, we will learn how to use RStudio user interface. In the previous segment, we learned how to produce dendrograms. In this segment, we will learn how to use RStudio to make graphs. RStudio is a free and open source integrated development environment for R. To demonstrate this, we will again use the default R dataset IDs. In this segment, we will show various RStudio layout of the panes. First, let us create a new R script. In RStudio, we can see 4 panes. Let us give a brief description of the panes. The first one is source, where we write R codes. Say, if we want to see header of IDs data, we write it in the source pane and press run. Console is the same as R console. If we wish, we can write the commands here one by one. All the submitted commands from source will be shown here with output, if any. Next pane contains file, plot, package, help. In the files tab, you can see the files of the working directory. Plots tab shows the plots when drawn. Package tab shows installed packages. All the loaded packages have check marks. If you want, you can even install and update packages from here. The last tab shows help files. The final pane is workspace or history. In the workspace, you can see all the R objects such as data, values, function. History contains the executed R commands. Let us see the dimension of the data. Let us save part of the data as iris2. We can see the executed commands in the console. We can find this data in the workspace. We can open the data in a separate tab and see it as an external window as well. All the commands go in history. Let us save various columns as various R vector objects. We can find all these objects in the workspace. We can even edit them from here. We draw a box plot using these variables. These plots can be seen in the Plots tab. We can see the earlier or later graphs from the toolbar. We can zoom the plots in an external window. We can export the graph to external files. The current plot can be removed if we want. We can clear all the plots from the Graph tab if necessary. When we want to see any help document, it can be seen in the Help window. In summary, we can use RStudio to conveniently work with R. Now, you will be able to use R via RStudio. This is the end of the section.